Is ComSci keeping you from your loved ones or stopping you from doing the things you love? Do you suffer from assignment anxiety, quiz queasies, or presentation paranoia? Well then boy do I have the solution for you! It's called the Breakpoint Debugger, and you can get it within your IDE today! With the Breakpoint Debugger, you can crack down on problem methods, watch your code execute, line by line, or keep track of nasty variables. And all of this for 10 easy payments of 0.00000000. Those are Bezos zeros! So call today and start debugging now. A message from the Government of Canada. Alright fellas, that's enough with the pre-roll today, I think. Just broadcasting some of those videos. Today we'll be doing like the basic sorting algorithms and stuff, and showing how this works in the debugger. As usual, there's a GitHub link, send it to the chat. You guys should see that, let me know if you see it. If you do not, there is a problem. We'll get that going, and in the meantime I'll show you cloning it. Where the bloody hell is my IntelliJ? I do not know, I've lost it. Oh, there it is. Alright, wrong thing, but it's okay. We can go get from version control, put the URL. Now already exists. Oops, open recent. There's mine. You guys can just clone it by getting from URL, no problem. Hopefully I am audible as well. Just gonna double check that. Am I audible? Yes, I am. Perfect. Alright. So in here we've got on the wrong monitor. Give me a sec. We've got the tutorial code, and it's empty. Great. Well, that's because we're creating a new thing. We're just gonna call it bubble sort. And in here we'll put our little method. Sorry, I guess I didn't have any code come up in there. Or did I open the wrong project? I might have. Oh yeah, that's why. No, that's not why. It's... There we go. Sorry, I opened the wrong project. It's this one. Here we've got a method. I'll check out the non-solution branch. There we go. And here we're supposed to write bubble sort for an array. And, well, bubble sorting an array is a simple concept. Not too many people in here today, but I'll still ask if anybody wants to participate and think about how they might sort an array. If not, I will proceed to explain it. I'll give you guys a second. Shout out to anybody who did show up. You guys are the true OGs. I think there might be like a Comp 206 thing going on right now or something. Probably. Anyways. Alright, so seeing as nobody is talking, I will continue to show you guys bubble sort. So bubble sort is a really simple algorithm. The point of it is it's supposed to just be like a direct comparison of different items in your data set, which you are, well, comparing to each other and slowly having them bubble up to the top, like as if it was literally just bubbles coming up from the bottom of a fluid. It's a very simple algorithm. It's very few lines of code, so I'll go into a bit of theory while explaining it. Bubble sort is one of the slowest sorting algorithms because what it has to do is it has to iterate through a bunch of different pieces of your data set. It's got to go through your array or your not array, whatever data set you want to sort, and it's got to compare every value to every other value and then swap them if they're in the wrong order. Essentially, it's the worst possible sorting algorithm. Today, the point of our demo is going to be in order to sort the colors in this window. So if it's the same window from before, if you remember it. But right now, these colors are kind of out of order. They're going to be sorted in order of brightness when we're done. Right now, they are sorted in order of nothing. So here you've got some bright colors, some dark colors, all out of order. We don't like that. We're going to fix that by putting them into order of colors. And then I'll show you guys how bubble sort works with the Breakpoint Debugger, and it'll be a fun time. So, first things first, when we're sorting this, we can start maybe with our for loops. So we can say for int I equals 0, I is less than, let's just say the length of our array, I++. Now we're iterating through this for loop, and we want to see if we can compare every single element of our array. Now, to get a number out of a color, we just do color.getRGB, not get HSB, color, get RGB. Oh, not color, get RGB. R0, for example. Get RGB, that's how you get a number of it. That's what we're going to be comparing. Later on, we'll learn about extending comparable, and that's going to be a fun time. So then we have to, I think, maybe iterate through this loop backwards. So maybe we can say for int j is equal to 0. J is less than I minus 1 j plus plus. And this is basically iterating through the part of the loop we've iterated to, if that makes sense to you. But these loops don't actually work right now. We actually have to have a number we can modify in the loop to kind of shrink down the thing you're working with over time. So we're starting out with a y boy, but if we actually get a smaller boy, we can kind of narrow down the array as we iterate through it. So as we go through our data set, we're trying to swap items that are in the wrong order, bubble them up to the top, and then work with the smaller subset of the array that's already sorted. So we'd have, for instance, let's say an array of 6 items. If we sort through, we start, let's say the bottom item is in the wrong spot. The bottom item will slowly bubble up, work its way up the array into the top slot where it belongs. And oh, it looks like my video's frozen. That's fantastic. You couldn't see my little demo there. Let's fix that. Oh, ooh. My video's popping off, isn't it? It's on. Give me a sec, I'll fix that. Alright, perfect. Just had to fix the video there for a second. So yeah, the point of this is it is the subset of the array which we are sorting. And this part is looping through the array, and this part is looping through the subset of the array. If that makes sense. It's not quite a divide and conquer algorithm like something like merge sort, but it's also not that, like it doesn't just iterate through everything. And then we also want to modify this for loop condition for us. So instead of the array length, we want to just use the subset of the array. So we can just do n minus 1. And then we can do n minus I minus 1. And this is just counteracting, or this is like implementing the fact that we're going through a subset of which part of the array we want to work through, if that makes sense. Now we just have a simple if condition. We're just going to say if our j is greater than our j plus 1, because the condition of having it sorted is that, so yeah, the condition is of a sort is that if one of the elements is, let me finish writing the get RGBs and then I'll tell you. So the condition of a sort is that every item is smaller than the item next, like the item after, right? So in a sort, it's like if it's 1, 2, 3, 4, 5, that's sorted because 1 is smaller than 2, 3 is smaller than 4. You know, you get the point. So if you go through with a for loop, you can then compare that every element is in fact smaller than the element after it, and that is a way to test whether something is sorted. We're kind of breaking down the problem into, is it sorted or is it not sorted? And then we're saying, like, well, how do you define sorted objectively? Well, the objective definition of sorted would be that every element is smaller or bigger than, which, you know, if it's sorted from smallest to biggest, every element is smaller than the one after. And if it's sorted from biggest to smallest, every element is bigger than the one after. You get the gist of that, I hope. So we're comparing that each item is in fact in ascending order here. And I'm doing it by comparing the RGB values, but you can also just do it directly with an int or whatever you want to do it with, right? And now we can just say a swap. So we can just say swap. I'm going to put it in a separate method, but we don't actually have to. Swap, and then we'll say r j plus 1. And now I'm going to make a little swap method for us. Ooh. Well, actually, I should say I'll do it like this. So now swap r j plus 1. And then here I can say color temp is r. Oh, input now. It's called input. IDX1. So that input IDX1 is equal to input IDX2. And now we can just say input IDX2 is equal to temp. Now, well, we'll see, actually, why this may or may not be a great idea. But to do so, we'll use a breakpoint debugger. So this should be a working version of bubble sort. But, you know, what if we actually run into some problems here? What do we do? Let's see if it works. It looks like it ain't doing its business. Or is it doing its business? I think it is doing its business, actually. But let's make sure. So if we actually put breakpoints into here, we can watch what happens over time. So I've breakpointed every method. By that, you just double click on the line in Eclipse, or you single click in IntelliJ, and then you run it with the bug icon. So you click the bug icon. Now, if I click on, let's say, hard, we can watch it. I'll make the window smaller so we can actually see the visualizer at the same time. Okay, so here we've got, oh, come on. I'll make this very visible for everyone. Actually, I will full screen it again. So, here we've got the subset, which is an array of length 6. And now we're looping through that array, and as we watch the course run, it's saying j equals 1. Okay, is this condition true? Maybe. Now it's going to go into a swap. Oh. Nice. And there we're going. So we can see R is color 6 at 2101, and it's slowly, as we run through the system here, moving these around. So you can watch, see where my mouse is here. You can see the colors in the array, and you can see as they slowly bubble up here. And even when we go into the swap method, you can see input 1 and input 2 are here. You can see their different color values, and you can see as we go, index 1 is 0, index 2 is 1. And then we swap them around, and to swap we just assign a temporary value. We swap the two places, and then we reassign it back to the original. We go through this repeatedly, and it takes a really, really, really long time. The reason it takes a really, really long time is that we have nested for loops here. We're working in O of n squared. For every single element, we're comparing it to every other element. It's about the least efficient we can get, except for like random sort, which is either more or less efficient than this, depending on the situation, because it's random. So now you can see it's gone through the sort, and it's sorted it darkest to lightest. Now, here, if we want to sort it lightest to darkest, all we have to do is swap our loop condition right here. We'll go into hard again, and we'll watch it run again, and we'll see it swaps things a bit differently this time. I'm just clicking through it really fast, but you can actually watch it go. You can see here it's swapping blue and yellow. A temp has been assigned to blue. So now you can see, oh, now at this line, both input IDX1 and input IDX2 are yellow. And then at the end, input IDX2 turns blue because that's what temp was, and then we're good to go. It's relatively self-explanatory, and if you want to take it slow, you can always specifically look through this section of the tutorial and follow along in your own IDE. And now we're swapping through, keep going. Here we're going to be swapping, which ones? We're going to be swapping yellow and gray, or we're not. Yeah, we're swapping yellow and gray, so temp becomes gray. Temp is storing gray, so that when you override it, when both of these are yellow, gray is still saved somewhere. And now gray is put back into IDX2, and we keep moving, keep sorting. It's very slow because it's bubble sort. And now we sorted it the opposite way. Corona. All right. So we've got a sorted data set right now. and we can sort it both ways. And that is fantastically advantageous for us, because now we have the ability to sort things. And I think I implicitly showed you guys, but I'll tell you guys now. Anything that you can kind of assign a number to, you can sort. So here I'm not sorting ints, I'm sorting colors based on their RGB. But I can also sort it based on any other numeric field. I can sort it based on the red channel, let's say. Red. And if I sort it based on the red channel, we can see that it's now going to be sorted in a descending order of redness. And now this one is, I suppose, the most red, and this one is the least red, if that makes sense, right? You guys can hopefully see, reddest to least red. And we could also do sorting in terms of blueness. Get blue. And we can sort based on any int value. And you'll see that a lot of the time in CompSci, you might need to sort based on different properties. Or let's say you have a situation where you can sort something, and then depending on what the value of certain properties is, you can sort in conditions where the values are the same. So for example, you could sort by how blue something is, and then if it turns out that it's all equally blue, then you sort out by how red it is, that kind of deal. You can do sorting and then have one sorting condition, and then when you have two things that are the same, you can make it a sorting condition which is different, if that makes sense. So again, yeah, you can view the sort through the debugger. That's the bug icon. And then when you click something to sort, it sorts it through. First thing it does is it finds n as the length of the array, because right now we're dealing with the whole array. N is 6. Then we loop through, we hit the inner loop. N is 6. We're iterating through, once again, the whole array. Except here it's going to be n minus 1. I is 0. N is 6. 1 is 1. So we're going to be going from 0 to 5. The reason for that is that here we access j plus 1. So we're basically looping through, and we're looking at two pointers. We're looking at the pointer to index whatever, and then the pointer to index whatever plus 1. So this loop will actually be looking from 0 through to 6. And then as we go through, we can identify that n will go up because, n will depend on which subset of the loop we're using. Oh, but I didn't even actually implement the n shrinking yet. That's oopsies. Yeah. So yeah, actually I forgot to implement the detail, which shrinks the n when we sort through elements. Oops. It's okay. I'll proceed with the demo here. So we go through, we loop through, we sort, we do bubbles. We can see colors change. Here we're looping through once again. JS3, yeah. And we're not swapping anything because these conditions are already passing. And that's another one of the great inefficiencies of bubble sort. It's that you hit already sorted elements and then you just keep twiddling away at it rather than sorting those particular elements. So that's that. And then, yeah, we can also see that, yeah, this sort is pretty simple actually. There's not much else to see. I'll remove the n bullshit because I decided not to use that. R.length. It's not necessary here. You can use it perhaps to optimize, but for today I will not be. It's just a difference from the notes. And then this should also run. I'll do hard mode today. And yeah. Should be sorting based on blue. And then we can do get RGB instead, and it'll sort based on the RGB value of a color. Yeah. Let's run it. Yep. I think so. And then RGB is the opposite. And we don't just have to sort by color, we can sort basically any kind of object. If you want to make an object that's not otherwise sortable into an object that is sortable, you can use the comparable method, or not the comparable method, the comparable interface, which is something we'll be getting into later in the course, but we could touch on it now. However, I think that that's a bit overcomplicated for now. Essentially, comparable lets you define how an item is to be compared to another type of item. It's similar to dot equals, except it also, instead of returning yes or no, it returns how much bigger or smaller it is than something else. Now, I can go into a bit of runtime efficiency stuff as well today, because we've got a bit of time. And if you guys have any questions, you're welcome to ask them away. Just interrupt the broadcast at any point if you have a question. I'll be happy to answer. Just trying to look for my runtime efficiency analyzer window. Where did I put that? It's not here. I'll open it somewhere here. File. Come on. File. Open, recent. Yeah, you can do it. I believe in you, computer. Okay, Comp250 final debugger. It's taking its time. It might be open somewhere else. It is. Oh. Yeah, give me a sec while the computer has its hissy fit, and here we go. We're back in business, I think. Alright, you guys can all see the screen. Yeah, you can. I've got my little preview over here. And this is the wrong window. No, I'm looking for the debugger. Where is it? Okay, here we go. Alright, so here I've created a little application. This was from last year. And this shows you runtime efficiency of different methods. And I'll go through and I'll explain kind of how runtime efficiency works, literally, like showing you the code. So give it a second while it creates its little databases, and then we can go. So here we plot a graph of how fast a method runs. And you can see that it's really, well, it's chaotic at the very start of the whole thing. It's kind of jumping up and down, and it's bad. That's also just because my computer is lagging to high hell, though. That's one of the problems with runtime efficiency is it's hard to calculate, especially if whatever you're doing happens to be a lot at the time. I'm right now using a lot of my CPU on random stuff, so that's probably causing some lag. But here you can see that as the data set goes up, this is the number of items in the, well, here's a hash table. So the number of items that are being sorted is going up. We are going to like 160, 165, and you can see that the number of nanoseconds it takes to run the sorting algorithm also proportionally goes up. But it's not always like a smooth graph, because sorting algorithms don't have a set runtime that's like, they don't have a runtime which is set in stone. They have a runtime which is like expected of them, depending on how the algorithm works. Like bubble sort, we can be pretty sure it's going to run in O of n squared, and that's because if you look at this graph over a really long time span, it's going to look like a parabola. It's going to look like n squared. Sorry I'm giving you a bad example here with this graph, because it's running so damn short. But if I do it like this, maybe it'll be more effective. Oh. Alright. This is merge sorting an array list, which is, it's an algorithm you'll see later. I just don't have bubble sort in these demos, because we kind of stopped using... Oh, actually, no. We do have an O of n squared algorithm here. Let's see if I can run it. And I'll post maybe a recording for you guys to show this stuff running in real time, because it's real slow right now on my computer. But you can see here, the yellow one is like bubble sort. It's running in O of n squared. That means for the number of inputs that you give it, it's going to square the running time, if that makes sense. You can see that the amount of nanoseconds it takes to sort, like let's say 80 inputs, is way more than it does for one input. It's just a terrible runtime. And you can see by comparison, they start off at about the same speed, merge sort and bubble sort, but then as the data set goes larger, merge sort, it still goes up. Like you can see when I showed you the graph of just merge sort, it's still slowed down when you add more stuff, but it's actually a factor of by how much it slows down the more stuff you add that affects the runtime efficiency. And here you can almost start seeing the graph of n squared. It's really spiky, but you can hopefully see the trend. It's literally like a parabola upwards that causes this. So yeah, that's kind of the idea of the runtime efficiency there. Going up, going up, going up, real slow. That should give you guys the point of it. And if you want to look at different kind of big O notation things, we've got O of 1 here, which, well, functions in O of 1, so that means that no matter how big the data set, it should take roughly the same amount of time. Or like get. These should both be around O of 1. Notice that they can take different amounts of time. Like this one is much slower than this one, but they still work in O of 1, which means that they still happen like the amount of time they take to happen is not varying by the size of the data set. You can see these lines are not, they don't have a slope. They're just flat. That's O of 1. If you look at, say, O of m, which will be O of, well, how many things are in the thing in a linear way, you can see that it goes up, but it goes up in a way that's linear based on the size of the data set. It's not as fast as O of 1 because it still goes up, but it doesn't go up nearly as quickly as something like O of n log n. So where's O of n log n? Here it is. Oh, actually, that's a bad one. Here, this one. Yeah, you can see that right away. The O of n log, or this one has a much worse big O notation than this one because this was just O of m, and this should hopefully highlight the differences for you guys. Like O of m or O of n means that you've got like a number that scales linearly. Then there's like O of n factorial, which is really high up. All of these just dictate how the relationship exists between how long it takes to run and how big the data set you're working with is. So yeah, that should hopefully clear up big O notation a little bit. And to show you guys how the code works, I think a good way to explain big O notation is to show you how this actually calculates this graph. And it's actually really simple. It doesn't look simple with all this code here, but it really is. Let me find it here. Twitter benchmark, here we go. So the stress test is very, very simple. If I can find one that is here, I'll find you a simple example. Okay, so I get a size, which is the length of the thing I want to sort. I create a data set of that size, which is what this code does. Like I randomize the data set. Then all I have to do is I have to do the method. Like here's the method that I'm doing. Object, method, and then the data set. All of this just generates something for the data set so you can ignore it. Really all I'm doing is I'm taking the start time before I ran the method, getting the time from the computer, and then I'm doing the method, and then I'm getting the time from the computer. That's all I'm doing. I'm just returning the difference. So all the running time means is literally you have a method that runs, you have the start time when you started running it, you have the end time when you finish running it, and then you just return the difference. That's how long the method took to run. That's all it takes. That's what the graph comes from. The graph just increases the size of the data set, which is slightly harder to do because you have to generate a data set yourself. But seeing as we have like a data set, let's say, actually finding the runtime is really easy. If you can have a data set that's growing all the time, it's just going to give you the runtime efficiency very easily because then you can create the x-axis. It gives you the y-axis based on running time. Hopefully that is clear for people. And then, yeah, if we look into the graph once again, which is still open here, I think. Yeah, we can see that the runtime efficiency really just depends on the amount of things. And if I turn on a turbo mode here so that I can, well, show you guys a much bigger data set, I can put on merge sort and slow sort and this bubble sort or similar runtime to bubble sort, O of n squared, and you can just see that as this is doing 1,000 for every size of hash table number, and it's just night and day the difference between a really slow algorithm and a fast algorithm. You can see that my computer is struggling really hard to even do the bubble sort for this data set. It's already in like millions and millions of nanoseconds running, and you can see that if I look at my like CPU usage on this, it's really, really high. Like this is basically using my whole computer to do a bubble sort, which it shouldn't do. It's like a really simple thing to do, and you can see that by comparison, the fast algorithm is just a line on the floor. It's not even doing anything at all. And here you can see it's completely pinned my processor on this core. It's just completely fully being used. There is no resources left for anything else. It is just dead. And that's because the algorithm is really slow. If I turn off the slow algorithm, now we're going to have a much faster time. You can see already with the same size of data set, it's still using the same amount of the CPU. It's still using the whole thing. But right away, we just passed everything we did before in like a second. It took us literally no time at all to pass the threshold we were at before with this fast algorithm, and that's kind of the difference it makes. We can see that the graph is already expanded to the point that we no longer have points on it. Like it's going really fast, and you can even start seeing the curve that it's supposed to make with this graph. So yeah, big difference here. That's the difference between a slow and a fast algorithm. Sometimes you'll see a spike or something in your algorithm. That just happens based on, well, I have a weird algorithm here that I wrote last year where it says fast sort, merge sort combo. That's why it's got a weird thing here. But you can see how visibly faster and slower different algorithms are. There's a lot of math involved too, but I won't go into the math, but I can explain the concept of why certain things are slower than others. Oh, and my computer is, wow, it's freezing. It must be running bubble sort in the background or something. All right, so if we look into here and we find an example of a situation where a method runs, I could actually maybe bring up the bubble sort as an example, as well as a fast sorting algorithm. So where's a fast algorithm? Give me a sec to find the structure of the program, and I'll find you a fast algorithm. We've got merge sort. All right, and merge sort is complicated. It's got a lot of different things, but one thing we can quickly see as like a rule of thumb that shows that merge sort is going to be faster than bubble sort is the use of for loops and the use of nested for loops. So usually you can be pretty sure that one for loop equals O of n. If you're iterating through your whole data set, that means it's going to be O of n. And you can also be pretty sure that if you have, oh sorry, my computer's being laggy once again. So if you have one for loop, you can be very sure that it's going to be O of n, O of m, at least. Like your best case with one for loop is going to be O of m. And then if you have a nested for loop, so if you have two for loops inside of each other, like we do in bubble sort here, then you can be pretty sure that it's going to be O of n squared. Because think about it. If n means you take a certain number of time for the number of things in your data set, that means that if you iterate through every single thing in your data set, that is going to take O of m time, just to do the iteration. Just to go through everything in your array, you have to take O of m. That makes sense, right? So then if you have to go through everything in your array, and then you have to go through everything in your array again, like bubble sort, it takes every element in the array, and it compares it to every other element in the array. That is no way to sort something, because we are taking an item and we're comparing it to every single other item. So not only are we iterating through the whole array once and looking at every single element, we're also iterating through the entire array all over again and then going through every single element. So it's just ridiculously slow. And the intuition behind a slow or a fast algorithm is usually just how many times do you iterate through your data set? How many times do you touch every element of the array? If you touch every single element of a data set, it's O of m, at least. If you touch every single element of the data set and compare it to every other element of the data set, you know it's going to be O of n squared, because for every single element, right, for every element, which there are m of, you have to go through m elements. So that's m times m times m times. That's O of m squared, right? And here, we can actually see that, because for every single element, and then again, for every single element, so this step would takes n time, and then inside of it, this step also takes n time. So therefore, this whole operation takes O of n squared, because you take n time n times, if that makes sense. So you go through n items in your data set, and since you're going through n items, you go through n of these items n times for every single item, and then you get O of n squared from that. Now if we look at merge sort, I'm not going to explain it in detail now. We're going to see it way later on in the course. But it's a much faster algorithm. And the short of it is that it does some magic that you'll learn about later in order to never actually access every single element of the array. It compares it by a bare minimum. It compares elements in a way where it doesn't actually have to go through and compare every element to every other element. Instead, it just compares groups of elements to other groups of elements. It's this complicated thing. It's a big algorithm. I'm not going to bore you guys with the implementation of this algorithm yet, but essentially it divides up the array. It sorts it based on groups of elements, and then that lets it, instead of going through every element, go through every group of elements. And then since it's going through every group of elements, then it takes a lot less time. And you can imagine that when you have, let's say, 10,000 elements, going through a group of elements will take you a lot less time than going through every single element. And it doesn't make a consequential difference when you're thinking about it in terms of like, will I get my data set sorted? If you have like 15 items in your data set, it will still sort with any algorithm that you want to put it at. But if you, so let's say, have 10 million items in your data set, O of n versus like O of n squared would be the difference between, let's say, finishing the algorithm in 10 seconds or finishing the algorithm in a year. It's like that huge of a difference it can make. Because again, the bigger your data set, the bigger the difference between algorithms becomes. And you can see that in the graphs I showed you, how with bubble sort versus merge sort, when we were doing 1,000 items at a time, the graph was like on the ground for merge sort, but for bubble sort, it was up in the air. Like the reason that we were going so slow was because bubble sort was holding us up that much. And you can imagine if instead of 1,000 elements, we did like 1,000,000 elements, or a billion elements, or however many, it would take just years for it to run, whereas merge sort could probably do it in a few minutes. And that's the difference between the algorithms, and that's why in computer science applications, when you're working for a company like, let's say, Google or Twitter or something, and Google has to sort through millions and millions of items every day. Well, Google is going to lose a lot of money if they use something in O of n squared, because if they have to iterate through every item compared to every other item, it's just going to take them forever. Their service is going to grind to a halt and stop, because when you start working with these massive data sets, it just doesn't work. So that's kind of the importance of the runtime efficiency thing. And then again, to get you an intuition for it, a for loop is, let's consider it O of n. And then a nested for loop, consider it O of n squared. If you have 3 nested for loops, considering it of like O of n cubed. Then if you're doing real bad, you could go O of n factorial, which is where it's just awful. And I could come up with some example of it, but there's so few algorithms that work in n factorial time. It's kind of like a joke at this point. Nobody uses. I mean, maybe you can come up with something which can only be done in n factorial time, but that would be really obscure. Most of the time, if you're working with something that's n factorial time, you are not doing it right. So yeah, that's a thing. Then there's also weird sorting algorithms like a random sort, where the best case is like O of 1, which is just impossible for a sorting algorithm, but the worst case is O of infinity. Like there's this kind of sorting algorithm too. And what I mean by best and worst case is that some algorithms perform differently with certain types of data sets. For example, if you have an optimized version of bubble sort, which doesn't make unnecessary moves, you can make it work really fast if you just have one element out of place. Like if one of your elements is in the wrong spot, bubble sort can be really fast, as long as you optimize it fully. This won't be very fast ever. This one will always be O of n squared. But if you make a better version of bubble sort, it will actually be speedy enough in some situations to be considered a fast algorithm. It's just most situations it's really terrible. And then you have an algorithm like merge sort, where it's fast most of the time, but there are situations where it's slower and there are situations where it's faster. Or an algorithm like fast sort, where it will divide and conquer your data set in such a way that if it's very badly missorted in the very start, it can actually take longer than a lot of other algorithms, despite the fact that it's considered very fast. I'm trying to think of an easy, intuitive example for you guys, but it's hard to come up with one off the top of my head for differently fast algorithms, or like algorithms that can perform differently fast on different things. But let's say, you could say that if you were to intuitively think of a sorting algorithm, like one you might use to say sort a deck of cards, if you ever have to sort a deck of cards, it might take you a lot less time to sort a deck of cards if one card is in the wrong spot compared to if every card is scrambled, right? Well, computers are the same. So if one element is in the wrong spot, it might take it less time or more time compared to if every element is chaotic. And for that reason, we have best case and worst case, and that's where big O and big theta notations come in. Those notations dictate whether it's a best case, a worst case, average case, all this kind of stuff. It's all got math behind it. But once again, the intuition should hopefully be really simple for you guys. It's just a matter of how many times you touch every element in the data set, how many times you mess around with everything that you are messing around with. If anybody has any questions, I welcome you to ask, though there's very few people here, so I don't know if that will be the case. But if it is, I will be pleasantly surprised. Very well. No questions it is then. Alright, so we've got the whole sorting operations going here. We've got bubble sort if you want to steal the code. I mean, it's not exactly very novel code. Everybody's got like 100 copies of this somewhere. It's a very basic algorithm, and you will use it. You'll have to use it soon in your courses, but it's not that great of an algorithm, and it's very simple. What else is important? Well, how to swap elements is also important. Like swapping, it might be something that's challenging for a lot of people, so I can go into a bit more detail explaining swapping. Alright, so when you swap elements, what you're doing is you have to replace one element with the other. But the problem is when you replace an element, you have to store a temporary version of one of the elements in order not to lose the data of the previous one. So if I run this with a debugger, and let's just do a medium sort, then I go through here, and I have to swap the red and the green. Well, if I put the red into index 2, then where does the green go? It disappears. Or if I put the green into index 1, you see index 1 will no longer have red in it, right? Because it's filled up with green. So I have to use a temporary variable to store one of the different things I'm swapping, so that I can then restore it into one of the other variables, if that makes sense to you. So I've got a temporary variable which is red, I've got a variable which is green, and I've got a variable which is red. Now I run through, and I swap them both to green. So now I still own the red, it's over here, so I can still put it back. And that's the point of the temp. So that's why there's this like 3-line swapping method. So here I'm swapping red and blue. So first step will be to save one of the colors. I think here we're going to be saving red. Right? Now red is saved. It's stored in this low variable, color temp. And now it's going to put back red into index 2 after blue is swapped in. So it puts blue to replace the red, and then it replaces it over again. Now I'll put a breakpoint at the last line there so that I can show you guys the final situation here. Yeah, and if we look at input, we can swap those around. So now I'll stop this and I'll rerun it with a different setup. And we can kind of watch the sorting work. So here, I don't know if I can zoom in. Can I zoom in for you guys? Actually, I think I can. Okay, so I'm zooming right in to this array. Give me a second. Alright, so now you guys should all see this very zoomed in. So now we start off this array. It's very chaotic. We can see the RGB values, which is what we're sorting based on. So now we go through. We do some swapping. And we can literally see watching it bubble up in real time over here. And this is the beauty of the debugger because it lets us actually view these things change. And there it's sorted. Let's do that again for you guys. So we'll do the hard data sets. So actually, we'll do the easy data sets so we have only 3 things to look at. So now watch our array. We have red, black, white. So we swap by elements. And now these 2 are black and we store white in our temp. Or no, we store red in our temp right here. See, red is in our temp. We swap these 2 around. We move forward. We put red back. It's in this spot. We run it again, and now it's sorted. That one is too easy to sort. Let's do a harder one now. We'll do medium. So we start with 4 things in our array: red, green, blue, white. And let's see, which ones are in the wrong order? Well, we need to swap red and green, because I guess red has a higher value than green. We run through, we swap those 2. So notice now, these 2 are both green. So where did red go? Well, red is being stored in our temp. Then red gets replaced in, and it gets swapped over. That's our first bubble up. That's our bubble rising. Then the bubble rises up, and now we're going to be swapping blue and red, because red needs to go to the top. Or maybe not the top, but we'll see where red goes. Anyways, it needs to go up. So now again, both are going to be blue. Red is swapping over. It's moved up. Now we're going through. Green is moving up, and now it's sorted. I'm going to change our data set now to make it a bit different. So I'm going to make this one yellow dot darker, yellow. Or here, I'll change it so we're sorting like a gradient, so it's going to be way easier for us to visualize. So we're going to do color yellow, comma, color dot yellow darker, color dot yellow dot darker dot darker, color dot yellow dot darker dot darker dot darker. And now I'm going to swap these around. I'm going to jumble them. So we're going to start off with, say, color dot yellow darker, darker, yeah, this one goes over here. It's completely chaotic. Then here I'm going to do color dot black. And now it should be relatively easy for us to see. I'm going to do a dot darker 3 times now, or 4 times here. Just going to make it really chaotic for us, but so that we have a clear picture of what it should look like. If I run it, our final sort, this is the wrong run. Okay, I'll run this one. This one can go away. So this one over here should run eventually. Alright, so which one did I change? This one. So now we can see that it's got a gradient, right? We can see pretty obviously how it's supposed to be looking when it's sorted. It's going to go from darkest to lightest, right? Awesome. So now if we run this with the debugger, oh, I'm sorry, I didn't full screen it for you. Okay, sorry guys, you couldn't see what I was showing you. There. So if I run this now, I've changed our colors to be a gradient. So it should be very easy to visualize how the sort should look. Now if I run with the debugger, we can actually watch it sort in real time. So we'll go hard, we'll look at our array. See, our array is completely jumbled and out of order. So we run through. Now we're going to be swapping, well, these 3, this bright yellow with this medium yellow. Swap them over, and we can just watch it bubble up. I'll zoom in again, like I did before, to our thing here. And I'll let you guys watch it bubble up. So here we've got, gradually over time you can see these elements are moving into their positions. This one is literally bubbling to the top and it's sorted. And now if we look back at our window, it is sorted. Run with the debugger again. I'll just go through it slowly one more time, and hopefully it'll be super understandable how this algorithm works, why it works the way it works, and all of this. We start off, it's terrible, it's out of order. In fact, you know what, before we run it, I'm going to change the ordering so that we have to sort more. I'm going to just swap this condition. And I'm going to rerun it with the debugger now. And by flipping the condition, I'm just telling it to sort backwards. And that will make it probably take a little bit longer because we have more things to swap over. So now if we look at our input array, it's completely not the way we want. We're swapping first the black and the bright yellow. Now the black is moving up. We can iterate through the swap again, and the black is moving down one more, and the black is slowly dropping down. You can see it's really slow because it's comparing the black to every other item, but the black started up here, and now it's moving down. It's down here. Keep swapping the black, and now it's all the way down at the bottom. Perfect. Now we can swap the next one. We're swapping this yellow and this yellow because this yellow's got to go to the bottom. So now those two are going to swap positions. Nice. Then we keep going through, and we keep swapping these guys, and eventually it runs, and we get our gradient exactly the way it should be. Super clear, hopefully, and I'll put breakpoints onto this one too. And we can really watch it run in full now. And we've got a data set that's really easy to visualize, I hope, with the gradient. So we've got an array, R, which is here. And I'll fit it to the screen again. Alright, so we've got our array here. We go through. We start off with the black at the bottom, and we bubble all the way through. We swap them. I'll take away the breakpoints from this method so that we just worry about the array. Then as the for loop goes, things bubble up. Black bubbles up first. Then this yellow bubbles up. Now it continues to compare every item. Even though it's already sorted, see, it's still comparing a lot. Or it's already almost sorted. Compares a lot of items, and it's done. It's good to go. So that's like n squared quadratic sorting algorithms for you. That's bubble sort. There are other quadratic sorting algorithms. I think insertion sort might be quadratic as well, if I remember my algorithms right. But bubble sort is the most popular of these sorting algorithms. And this is it working. This is it implemented. If anybody has any questions, I would be happy to answer. But hopefully it was simple enough. Here I've shown you guys the runtime efficiency system and how if you check runtime efficiency of different things, it takes different amounts of time to run different algorithms based on how big the data set is. And that is that. For now, I'll just leave this up with comparing merge sort and bubble sort, just to show you guys. Oh, actually, I'll put in all the common runtime notations. So we've got O of m, O of 1, O of n squared. Do we have an n factorial anywhere here? I don't think we do. No, we have no n factorials here. So in the blue, we have O of n squared. In the orange, we have O of m. In yellow, we have O of m log m, I think, or O of log m. And then in the bottom, we have O of 1. So you can just see the difference here. Maybe I'll do a better O of m method, one that is less bad. There. Oh no, that O of m method sucks. Did a bad job on that one. Okay. Here we go. This should be O of m, O of n versus n squared versus log n versus O of 1. And you can see that this n squared, which is bubble sort, just takes off right away, goes into the stratosphere. And yeah, if anybody has any questions, you're welcome to ask. For now, I'll just be rubbing in how shitty bubble sort is using this graph. And then I'll turn off bubble sort and show you guys the other notations. If you have any questions, ask away. If not, well, thank you for coming. You guys are the real OGs for showing up to this one. I think there's a Comp 206 exam or something going on right now, so basically nobody could come. But that's fair enough. Hopefully everybody did well. And yeah, fun stuff here. Again, O of 1, log n, m. Fairly well.